Swayam Prabha. Digital India. Educated India.
We have already seen that it is essential to have some control over the input to an engine to ensure that it runs at the desired operational speed when the maximum efficiency is achieved. We have also gone through a quick classification of the different types of governor mechanisms which used to be in practice or which are also used sometimes. And today what we take up is the commonly used governor mechanisms based on speed, that is centrifugal force, and controlled by gravity. So I have mentioned also to you that the first ever governor mechanism, which was designed by James Watt for his steam engine in the 17th century, was also one of the governors belonging to this class, that is centrifugal governor, but controlled by gravity. The three commonly used gravity controlled centrifugal governors I will just indicate here. These are the basic schemes of three different types of gravity control centrifugal governors. This is the familiar Watt governor. Where these are the spherical balls which try to fly off when it rotates, and that tends to move the sleeve up and down, causing the lever which operates the valve mechanism to control the input energy or input power to the system or engine. A little variation of this, it has certain difficulties, particularly at higher speed levels. Watt governor tends to become insensitive. So, to improve its sensitivity and performance, the next improvement was by Porter, and we call it Porter governor. Here the only difference we find is, real main difference is that there is a heavy weight, not just the sleeve, and this weight can act as a controlling agent, and you can see later that it can improve the efficiency or rather improve the sensitivity at a higher speed level. But basically it is therefore a Watt governor with very slight difference. Now, one thing we should also mention, whether it is used on the axis or away from the axis, all these things are matters of details and vary from one case to another. But to improve this sensitivity further, the change was made, and we have Proel governor. Here the spherical balls are not placed on this pendulum like a member, but instead it is on the lower link, which is extended beyond the hinge point here, and this sphere is mounted on this part of this extension. This improves the efficiency further, and here of course we also have a central weight to control through gravity. So, this provides much higher sensitivity. So, these are the developments through ages. This is the lower sensitivity. So, what we will do now, we will take up the analysis of Porter governor and Proel governor. What governor we will not do, because there is not much difference with this, only whenever we can make this weight of the central mass kept here as 0, it becomes same as a Watt governor. We will draw only one side, because the whole thing is symmetric, and we will therefore draw also only one side. So, we will take up the case, which is a particular case where this length is 0 and the spherical mass is kept here, that means they are both hinged here, and sleeve is here, and this case is symmetric in the sense that here this distance is E, here also it is E. The lengths of both the links are same, L. We call this end as B, and at this particular situation the radius at which the balls are revolving around the central axis is r. Makes an angle theta, and obviously this angle will be also theta. We can also see from our kinematics we can find out that this point moves in a direction which is perpendicular to this, and this point of this link moves in this direction. So velocity of this point has to be along this, velocity of this point will have to be along this. So the instantaneous center at this point of this link is at I. The forces which are acting the weight of the ball, and of course here if the mass of this is mg, but being there are being two sides, it only half will come to this side. These are the external forces. Internal forces we can designate, that means tension in this we can say TU, the upper link, and tension here in this we can call tension in the lower link, and obviously tension in the lower link here and here they will be equal and opposite. Now what we do, let us take the moment of the forces acting at B. Now what we can do, that effectively the control force we know, which we have always assumed to be a force representing all the restoration mechanism like gravity here, to be acting as a force in this direction. So if that be the case, then if we take moment about point I, F into BC is the perpendicular distance, will be equal to mg. How to find out this? Mg is the force here, and moment about this will be IC plus TL into IB. This is IB, and this is theta, this is theta, that means this angle is 2 theta, so it will be to explain it further, that means this point, that means moment of this force TL will be TL into the perpendicular distance from I, which is this, and if this angle is 2 theta, then this is nothing but IB into sine 2 theta. That's what it is. So the control force, that means this force, what are we doing is that we are trying to find out an expression of the control force. Now control force means, that means on this sphere the effect of control force will be representing the effect of other forces. What other forces are acting on this? One is the gravity, one is TL, one is TU. So therefore if we take the moment about this instantaneous center, the moment of the actual forces acting on this sphere must be equal to the force or moment what would have been produced if this all these forces represented by a horizontal force. So, therefore, this into BC will be same as the moment of the other actually acting forces about this point. So, moment of TU about this point is 0 because it is passing through point. Moment of this is this and moment of this weight is this. So, the control force F can be expressed as IC by BC, this is IC and this is BC. So, IC by BC is nothing but tan theta, this is theta, because this length is L, this length is L, this length also becomes L, because this is symmetric, this angle and this angle they are same. So, therefore, IC by BC is nothing but tan theta, which is this, and IB, that is IB by BC, IB by BC is nothing but cosine theta. So, this cosine theta is, sorry, BC by IB is cosine theta is the denominator. We also know, now therefore, the question is how much is TL, that is still not known. But if we consider the equilibrium of this TL and another TL on this side, they are supporting this total weight mg. So, we know that 2 TL and what is the vertical component? Cosine theta is equal to mg. And using this, finally we get the control force, which is a function of R, is equal to now, of course, we have to write in terms of R. So, we can write this as G, and tan theta we can write tan theta, what we are writing, this length is how much? It is R minus E is this much. How much is this? That is L square minus, this is R minus E square is this. So, this by this is nothing but tan theta. So, that is what we have written, and therefore, now F is expressed purely as a function of R. There is no other variable there. Now, for any speed, the equilibrium is established by the condition that this control force must be equal to the tendency to fly off, that means the which we call centrifugal force, they must match. So, therefore, we get a relationship between the speed and so this is just to equate this with this and find out omega square, you will get there is hardly any calculation involved. So, now we get that for a given speed omega when it runs, the equilibrium value of the radius at which the sphere must be, and correspondingly the location of the sleeve will be. Now let us plot to see how the control force looks like for this particular type of governor, a Porter governor, and with this kind of configuration. So we have an expression for the control force as a function of R. So one thing is clear, that when R is equal to E, Fr is equal to 0. So it starts at a location which we call R is equal to E. And then it goes, and it becomes infinite when the denominator is 0. That is, R minus E is equal to L, or R is equal to E plus L. It tends to become infinite. And this is the control force curve for Porter governor with this kind of configuration. So therefore, we find that if we now plot the centrifugal force, which will be just a line for a particular omega, and the slope of this line will depend on the omega, because the slope is nothing but m omega square, and this will be the equilibrium position. If the governor rotates at this speed, then this radius at which the balls will be this intersection. And we also find here, that means two things. Let us see the characteristics. One is F equal to 0 when R is equal to E, and F tends to infinity at R equal to plus L. And this diagram makes it very clear that whatever may be the speed of rotation of the governor, and at the intersection point, that means at the equilibrium position, the slope of the control force curve is always more than the slope of the centrifugal or the deflecting force curve, and that is the condition for stability. So it is stable throughout its range. The governor will be stable all along, we do not have to worry. Only one thing we can discuss here quickly, that this situation, this derivation is fine. Only one thing we have not been able to take up, and let us take up that. We have not considered, that means when the sleeve moves, we have assumed perfect, no friction, perfectly smooth situation. But in reality, it is not the case. There will be always certain amount of sliding friction involved, because it is a sliding motion of the sleeve and the central weight along the central rod, which is the central axis of the governor. So when it is speed is increasing, what will happen? It will try to move off, and so the friction, whatever friction there may be, so when it is speeding up, that means speed is increasing, then it has a tendency to move up, it has a tendency to move up, and so obviously sliding friction on the sleeve will be acting in this direction. This is the friction. So what is the effect of friction on the whole thing? You will find effect of friction is nothing but to add to the mass m here. So therefore we will get that if we add, that means so that the total force in this direction is mg plus f. So each one will be then having mg plus f by 2. As a result, the control force curve will appear to I am exaggerating, of course. So, suppose at that instant it is speeding up. So, the control force curve, the force will be here, which is, this is the total force F, and you have to add certain amount which is here. So, what you will find there, that omega u square, that means when it is going up at the upper limit, at this particular rotation, therefore radius, that means the governor will be at one location, though the speed may vary, because the friction will take care of that variation. So, at this radius, when the governor is rotating, what is the maximum speed at which the governor can still be at this location is this point. So, this will be your upper limit of the speed at which the governor can remain at this radius r. Similarly, what is the lowest possible speed when the governor so therefore there is always certain amount of insensitivity, that means the speed of the governor can change from omega L to omega u, but still governor will remain at the same location. That means it becomes slightly insensitive. We can find it out that this will be, as I mentioned, G into 1 plus the effect of the friction force will nothing but to add the force in this direction. So, total force is mg, which will be now mg plus f. So, therefore, what we do, we add m plus f by g, because g has been taken out. So, the expression for the upper speed limit will be this, and when we try to find out the lower speed limit, that means the speed is decreasing in this direction. When speed is decreasing, this tends to move in this direction, and obviously then sleeve wants to go in this direction, and obviously friction force acts in this direction. That is, now it opposes the weight, so it will be mg minus f. So, this upper limit can be found out from the same expression, only when mg is replaced by mg plus f, then what it is going to be? G into m plus f by g. So, m will be replaced by m plus f by g. Similarly, when mg is replaced by mg minus f, when speed is decreasing and sleeve is going in the downward direction, then this will be, m will be replaced by m minus f by g So, we get the upper and lower speed limit at a particular operating radius, and what we can do, therefore, we can find out the insensitivity omega u square minus omega L square by omega square is equal to, now if we subtract that and then divide by omega. Omega is the mean speed, where so you will get, this will be simply 2f So, omega u minus omega L by omega, if you use this, will be approximately equal to f by, and this is called the coefficient of insensitivity. Or detention by friction, both are used. Effectively, friction is making system little bit sluggish in the sense that the governor configuration does not change just by any amount of change in speed. It remains static for a particular range of speed omega u omega L, and obviously you can see that how much will be the insensitivity will depend on this particular ratio, that means the difference between the speed divided by the operating speed or average speed, which is this, and when f is 0, as you can see, it is directly proportional to the friction force. Next, let us take up the other governor, that is the Proel governor. That is again an improvement on Porter governor. Let the particular situation and our representative control force, which is a hypothetical force as if acting in the radial direction, is like this. Let us give names to various points. So let this point be, so in this particular case we have kept it hinged about on the axis, but in a particular situation it may be even away from the axis. That each and every case has to be solved separately. This point called C, and this point is say C prime, and let this gap be equal to E. This point is say B prime, this point is say B. So the instantaneous center will find out as before I, and this point is D. So this is a particular situation at a particular speed, and here of course the force is acting on this, and that is half the sleeve load, because there is the other half will act on this side. So here what we have in this particular case, again if this we take the moment of this representative force F about I, it is F into BD. BD is the distance, perpendicular distance from the point I. This must be equal to, but actual force acting is mg of the, if you consider the whole system here, then any force acting here will pass through this, its moment will be 0, but these two forces moment you can take. So it will be mg into id plus mg by 2 into I, and therefore the control force, which is a function of R, will be actually mg into id by bd Now, in general, of course, we may not be able to write nice closed form expressions for these ratios when the symmetry etc. are somewhat lost. We could do it in the case there because both the points were located here, the lengths were equal, all kinds of symmetry conditions were satisfied. But in general it may not be. So best thing is to draw and then measure these dimensions and find out the value of f at that particular configuration when it is at a distance r. This is actually instantaneous radius of rotation. And at equilibrium, we know that the condition is that f will be equal to so if we at a particular r, if we can find f, we can find out what is the speed at which the system will remain stable at that particular radius. Best will be to take a particular example. Let us take an example. We take a particular case where AB the two linked lengths are same and say there that much. The value of E is 3.8 centimeter. The extension B prime B on which the balls are attached is the mass of the rotating balls is equal to 4.8 kg and the sleeve weight so it gives some idea about the order of magnitude of the values involved, how heavy. So you can see these are huge systems, because a very large engine has to be controlled. That means the whole lever mechanism has to be operated. So you need very substantial magnitudes. It is also mentioned that at so what we have to do is we have to determine the equilibrium speed at r is equal to 16.5 centimeter and r is equal to 21.6 centimeter. So this example will tell us how to handle such problems. Let us first try to find out what will be the equilibrium speed when the radius of rotation is equal to 16.5, which is the minimum position, and also when this extension of this lower link B prime B is parallel to AC prime, that means the governor axis. How to draw it? It is best solved graphically. To solve it, first we select any point as the center of the ball. Since we know that B prime will be vertical, that means parallel to the governor axis in this lower position, what we do, we draw a vertical line and whose length point B is given, B prime is given because this length is 10.2 centimeter. So we can find out this point. Now we know the distance of this ball from the governor axis. So this length is 10.2 and this line we draw which is at 16.5. That is the value of r at this instant. Now draw another line on which point C will be located, and we know that it will be at a distance 3.8 centimeter from the governor axis. Next, you know that point C will be at a distance 30.5 centimeter from B prime. So you can easily cut this length to make this point C, and obviously you cut this point to get A, both 30.5. It is not to scale obviously. So once it is done, then we extend this, draw a perpendicular, you get I, you get D. So now you can measure, so if you can do it, we will find that ID comes out as 17.2 centimeter, IC is equal to 29.8 centimeter, and BD is equal to 37.6 centimeter. So with these values we can substitute here. We know small m, we know capital M, and we know IC, ID and BD. So therefore F can be found out easily, and from that obviously we can get this equation. So what we will get, that omega square is equal to 16.9 radian per square radian per second, and which will ultimately give us RPM to be at R is equal to 16.5. Now if we go to the other value, R is equal to 21.6, then how to solve it? We have to again draw this, and to do that what we do is, this is the governor axis, and at a distance of 21.6, somewhere we put the sphere, point B. We also know that point C will be located on a line which is 3.8 centimeter. Now one thing we should notice, that in Proel governor this is one rigid link. So therefore this distance BC also remains constant. This angle cannot change, it is one rigid link, and we have already found out this distance BC from this first drawing, and which is going to be the same for each case. So, we can now cut this point C by measuring this PC as this PC. So, once this is known, then obviously the point B prime can be easily found out by drawing the triangle. This will be 30.5 centimeter and this will be 10.2 centimeters. So, from these 2 points I can easily find out this location, and obviously now I can find out this location A. So, actually I should have used black. And then the other dimensions can be found out. This will be I, this will be point D. We will find that ID is equal to 20.2, IC will be equal to 38.8, and BD will be equal to 35.4 centimeters. And when these things are substituted in this control force expression and equated to the centrifugal force m omega square r, we find omega comes out as 18 radian per second, which is equivalent to n is equal to 171.5 rpm. So, therefore, we can find out the equilibrium speed for various radii at which the sphere can rotate in a stable manner. I think this will be enough for our discussion of gravity controlled centrifugal governors. Now, I think next we will go for further improvements which have come here. We can see that we have certain disadvantages if we depend on the gravity for all our controlling operations. To have large force, we have to have a large mass, it will make the system heavy and so on. On the other hand, as I already mentioned in the previous lecture, that much better control, the system can be much more compact, lighter, etc., when we use springs for controlling the governor mechanism. So, next we will take up the spring controlled centrifugal governor.